Hello friends, IBM is here with another episode of Learning Physics, and do not forget to share these videos with your friends. Do not forget to download the document of past paper questions to use it for this learning series. We are dealing with solved past paper questions, that is AS Physics, and specifically these are questions from paper 2. These are questions from paper 2. And remember, we recently introduced dynamics, and this is going to be dynamics part 2. This is the second series. I think there will be 3 parts for dynamics. And we saw part 1. We saw the questions in part 1. Remember I said in dynamics, we are going to deal with what affects motion. In other words, we shall be concentrating on Newton's laws of motion. We shall be concentrating on questions about linear momentum. But remember I said there is no clear boundary between most of these topics. So some questions will have some parts in dynamics, some parts in kinematics, some parts in work, energy and power, some parts in other units. So you'll bear with that. There will be no clear boundary between these units. So without wasting any time, let's go to the past paper questions in our document. So I think in part 1 we stopped on page 154. And I wish to start from the same page. We stopped on this same question, state Newton's first law of motion. And we said the first law of motion states that a body continues at rest, that is if it was at rest, or moving with a uniform velocity unless acted upon by a resultant So a body continues at rest or moving with uniform velocity unless acted upon by a resultant force. And I mentioned that the word resultant is going to be very, very important here. The box slides down a slope as shown in the figure. Of course, before we go to the questions at this point, as a physics student or even a math student who is doing mechanics, you could straight away come up with the forces acting on this box. First of all, its weight acts vertically downwards. This is its weight, which is going to be m times g. Secondly, you expect that the weight, because this angle is theta, the weight can be resolved perpendicular to the plane, and perpendicular to the plane, that is mg cos of 20, because this angle is going to be 20, and down the plane it is going to be mg sine of 20. Of course, there is a normal reaction force R upwards. So we can now look at the questions. We can now look at what the questions are. The angle of the slope is to the horizontal is 20 degrees. The box has mass 65 kilograms. So that means m is 65. Remember, g is not grams, it is acceleration due to gravity. The total resistive force R on the box is constant as it slides down the slope. So if it slides down the slope, it means the resistive force must be upwards. So I'll call it R. So I can't call this R again. The reaction, I'll not call it R, the normal reaction. Maybe I can call it FR, because the resistive force is already called R. If it is sliding down the slope, the resistive force must be up the slope. State the name and directions of the other two forces acting on the box. Of course, it has a mass, it has weight. So the first force is weight, and the weight is vertically downwards. Not just downwards, the word vertical is going to be very important here. And number two, we also have another force which I call Fr, that is the normal reaction force, which is perpendicular to the slope. The weight is vertically downwards. The weight is not normal to the slope, it is just vertically downwards. Then we have the normal reaction force, the normal reaction or normal reaction force, which is perpendicular to the slope. So the normal reaction force acts at 90 degrees to the slope. That is the second force. So those are the other forces in addition to the resistive force. The variation with the time t of the velocity v of the box as it moves down the slope is shown in the figure. So this is the variation of v with the time. Of course, we know that if this is a graph of velocity against time, the gradient is the acceleration. The area under the graph is going to be the distance or the displacement, whatever. Use data from the figure to show that the acceleration of the box is 2.6. So we now know that acceleration is the gradient. Or I can just get change in the values of v with the time. So acceleration equals to the gradient. Oh, it is equal to the change in the values of v, that is v minus u divided by the change in the value of t. I was called delta t. So this is going to be equal to, so I can start with, I think this is 6.0, this value here is 6.0, and this value here is, because the scale on the vertical is 2.0 divided by 10, that's 0.2, so it means this is 0.8. So this will be 6.0 minus 0.8 divided by the change in time, which will be 2.0 minus 0. So when I press my calculator, so from my calculator, I'm getting 2.6 meters per second squared. Calculate the resultant force on the box. Resultant force. We know that the resultant force F is equal to mass times acceleration. The resultant force is mass times acceleration. So the mass, they gave us the mass was 65. So this is 65 times acceleration, which you have got 2.6. And from my calculator, this gives me 169. Then determine the resistive force R on the box. Resistive force. Remember, the body is moving downwards, and it is the resultant force which causes the acceleration. So resultant force M, which is MA, is the difference between the force downwards and the resistive force. And the force downwards is mg sine 20. The resistive force is upwards, which is R. The resultant force is the difference between those two. So the resultant force F is going to be mg sine of 20 minus R. But remember, the resultant force is 169. So I'll say that 169 is equal to mg, which m is 65, times g, which is 9.81, sine of 20 minus R. So when I make R the subject, R is going to be 65 times 9.81 sine 20, which is 218.1 minus 161. Minus 169. So I'm getting R as 49.1. So that is approximately 49 newtons. Two balls X and Y are supported by long strings as shown here. The balls are each pulled back and pushed towards each other. When the balls collide at the position shown in the figure, the strings are vertical. The balls rebound in opposite directions. The figure shows that data for X and Y during this collision. All X, Y masses are given, velocity just before collision are given, velocity just after collision are given. The positive direction is horizontal and to the right. So to the right is positive, therefore to the left should be negative. Use the conservation of linear momentum to determine the mass m. So we want to determine the mass of ball y using conservation of momentum. First of all, we know that momentum is equal to mass times velocity. And by conservation of momentum, total momentum before is going to be the mass of x, which is 50. I will not convert the units because I know they will cancel out. 50 grams times the speed before collision is 4.5. That is to the right, plus. The other one is to moving to the left. So I will put minus. The mass of the other one is m, it is not known, times its speed is 2.8. Because the velocity is to the left in the opposite direction, that's why I have this minus here. That is total momentum before collision. Then after collision, the mass of x has the masses do not change, so that is 50 grams times its speed after collision is negative 1.8, meaning it is to the left, plus for y the mass is still m times its speed after collision is positive 1.4. That means it is to the right. So we simplify this. And collect like terms. So I will take m the other side and I will bring the other on this side. So I have 50 times 4.5. So this side I have 225 plus. I'm bringing this one also to the left, 50 times 1.8. Because it was negative, because of the minus there, it becomes plus 90. Should be equal to. On the right, I have 1.4 m plus 2.8. So that is 1.4 plus 2.8. So this is 4.2 m. So what is m? So 225 plus 90 divided by 4.2. So I get m as 75. Remember, I didn't change the units. So m is going to be 75 grams. Okay, state and explain whether the collision is elastic. We can check this easily by looking at the relative speeds of approach with the relative speeds of separation. So we can see relative speed of approach, that is the speed with which they are moving towards each other. This is the speeds of approach. So we have relative speed of approach is 4.5 minus negative 2.8, which is 4.5 minus, which becomes plus 2.8. Relative speed of approach is 7.3. We can check relative speed of separation irrespective of the direction. I would say 1.4 minus negative, or which becomes plus, or minus negative 1.8. So relative speed of separation is 1.4 minus negative 1.8. which is 3.2. The word relative, you just subtract the speeds. I could also have started with a negative 2.8 minus 4.5. I would still get the same magnitude, although it would be a negative. Just like here, I would have said negative 1.8 minus 1.5, I would still get negative 3.2. So we are seeing that the relative speed of approach is not equal to the relative speed of separation. Relative speed of approach is not the same as relative speed of separation. Relative speed of approach is not the same as relative speed of separation, so inelastic. So the collision is inelastic. Alternatively, you can check kinetic energies. You can check the kinetic energies. Total kinetic energy before collision is going to be equal to a half. I'm just checking kinetic energies. So before collision, it is going to be a half times the mass is 50 divided by 1000, 0.05 times the speed 4.5 squared plus a half times the mass of m is 75, which is going to be 0.075, I guess 75, 0.075 times its speed, which is 2.8 squared. This is total kinetic energy before collision. So a half times 0.05 times 4.5 squared plus a half times 0.075 times 2.8 squared. Total kinetic energy before collision is 0.80 joules. This is before collision. Then after collision, it is a half times 0.05 times the speed is 1.8 squared plus a half, the mass is 0.075, the speed is 1.4 squared. So I check this again, 0.5 times 0.05 times 1.8 squared plus 0.5 times 0.075 times 1.4 squared. So this is giving me a 0.15 joules. So you could also say, after checking this, you could also say inelastic, total kinetic energy before is not the same as total kinetic energy after. Total kinetic energy before is not equal to total kinetic energy after. So the collision is inelastic. Use Newton's second law and third laws to explain why the magnitude of the charge, the change in momentum of each ball is the same. I look at the mark also. The magnitude of the change in momentum of each ball is the same. They said using Newton's second law. Remember, Newton's second law is force is equal to mass times acceleration, which means force is the rate of change of momentum. And remember, third law, the force on body A due to body B is equal but opposite to the force on body A, body A by body B. So by Newton's third law, By Newton's third law, the force on X, is equal and opposite to the force on Y, or the force on X by Y is equal and opposite to the force on Y by X. That is by Newton's third law. But remember, force is the rate of change of momentum. Force equals to the rate of change of momentum. Force equals the rate of change of momentum. That is by Newton's second law. Force equals the rate of change of momentum. In bracket, this is by Newton's second law. Force is the rate of change of momentum. And remember, when I say rate of change of momentum, that is change in momentum with time. And the time of collision is the same for both balls. Time of collision is the same for both balls. Hence, change in momentum is the same. It is very easy to notice by Newton's third law, the force on X is equal but opposite to the force on Y. And remember, force is the rate of change of momentum. That means the rate of change of momentum of X is going to be equal to negative rate of change of momentum of Y. And remember, the time is the same, so time cancels out. So you remain with change in momentum of X is equal to the negative change in momentum of Y. The change in the negative just shows that the change is in the opposite directions. Okay. A gas molecule has a mass of 6.64 times 10 power negative 27 kilograms, and its speed is 1,250 meters per second. The molecules collide normally with a flat surface and rebounds. That is the most important part. When a particle, an object rebounds, it means it moves just in the opposite direction to its initial path. Calculate the change in momentum of the molecule. So we want the change in momentum of the molecule. At this level, you note that momentum is mass times velocity. So we want the change of the molecule. That is very easy. So the change in the momentum of the molecule is going to be the mass. It's not going to be changing. So the mass is 6.64 times 10 power negative 27. But the velocity is going to be, it is moving towards, it rebounds with the same speed. So the velocity is going to be 1,250 in the initial direction minus the opposite direction since it rebounds minus negative 1,250. So it means this becomes plus. When I press my calculator, so from my calculator, I'm getting this as 1.66 times 10 power negative 23 Newton seconds. Use the kinetic model to explain the pressure exerted by gases. Use the kinetic model to explain the pressure exerted by gases. This is a question not of AS anymore, but just for completeness, I'll answer. It is a question that we answered in ideal gases and ideal gases. We answered such a question, but we shall still answer it here. So a molecule will collide with the wall as illustrated in the previous part. And what happens? It rebounds. When it rebounds, there's a change in momentum. Remember momentum, remember the force is the rate of change of momentum. So since there is a change in momentum, the change in momentum with the time is going to be the force exerted on the wall. Remember, there are several other molecules, and the sum of all their collisions per unit area will constitute the pressure exerted on the gas. So we know that the molecules collide with the wall and there is a change in momentum. Molecules of the gas collide with the wall, and there is a change in momentum. And of course, by Newton's second law, the change in momentum over time is the force exerted on the wall. The change in momentum over time is the force exerted on the wall. Of course, since there are several molecules, the sum of all the molecular collisions, the sum of all the molecular collisions per unit area of the container, or per unit area of the wall, or per unit area of, okay, let me just say per unit area, not per unit area of the container produces the pressure. We fully answered the similar question in A level. We saw how a gas exerts pressure. When a molecule collides with the wall of the container, it rebounds. There is a change in momentum. The molecule experiences an impulse. The wall also experiences an equal but opposite impulse according to Newton's third law. There are several such collisions. So several such collisions average out to exert a force on the wall, and the force exerted per unit area of the wall or per unit area of the container is the pressure exerted on the container. Explain the effect of an increase in density at the constant temperature on the pressure of a gas. Increase in density at a constant temperature. So the temperature is not increasing, but the density is increasing. So if the density is increasing, it means we now have more molecules per unit time, or per unit incident per unit area. So if we have more molecules, then it means we are going to have more collisions. And if we have more collisions, it means we shall have a greater pressure. So we have more molecules, even though the temperature is constant, but since we have increased the density, how do we increase the density of a substance? By increasing the number of molecules. So increasing the density means more collisions per unit time. So we have more molecules per unit area, which means more collisions per unit time. So greater pressure. Yeah, increasing the density would mean more molecules per unit area, which means we now have more collisions per unit time, and therefore we expect a greater pressure. State and explain whether linear momentum is conserved during the collision of the ball with the floor. Of course, if we go back to the collision, we notice that the ball rebounds with the same speed. So it means that the total momentum of the ball and the flow before is going to be equal to the total momentum of the ball and the flow after. So it means momentum is conserved. And since the ball and if the ball and the flow, if the molecule and the flow are isolated, if the molecule and the flow are an isolated system, then we can believe that total momentum is conserved. So I think this question is misplaced, because this is a molecule and this is a flat surface. Molecule and a flat surface, and yet here it is referring to a ball and the floor. I think it's a misconnection, but let's just take it to be a molecule and a surface. So the total momentum Okay, so I'm going to just take the molecule and the flow. So I'll say total momentum, not even the flow, the molecule and the surface, total momentum of the molecule, total momentum of the molecule and the surface is equal. So this is before collision. Remember, the surface cannot be moving, it is the molecule which was moving. So total momentum of the molecule and the surface before is equal to total momentum of the ball and flow after collision. So momentum is conserved. Sorry, total momentum of the molecule and the surface before is equal to total momentum of, I want to be specific, although the question says ball, the previous part is showing a molecule and a surface. So total momentum of the molecule and surface after collision. So momentum is conserved. For an isolated system of interacting bodies, the total momentum is always conserved. So in next question, state the law of conservation of momentum. This I have just mentioned it. The total momentum total momentum of an isolated system So the total momentum of an isolated system of interacting bodies is always constant. So that is the principle of conservation of momentum. Two particles A and B collide elastically. Of course, we know what we mean by it colliding elastically as illustrated here. A was moving, B was at rest in the x direction. After collision, we see V moves at an angle of 60 and B moves at an angle of 30. So after collision, momentum is in two dimensions. The velocity of A after the collision is VA at 60 degrees, the x direction, as we have seen there. The velocity of B after the collision is VB at 30 to the x direction. The mass m of each particle is 1.67 times 10 power negative 27 kilograms. Explain what is meant by the particles colliding elastically. Of course, if they collide elastically, kinetic energy is conserved. So here, kinetic energy So the only thing which distinguishes elastic collision and inelastic is kinetic energy being conserved for elastic. So if the particles collide elastically, then kinetic energy is conserved. That is, total kinetic energy before collision is the same as total kinetic energy after collision if they collide elastically. Calculate the total initial momentum. We know that momentum is mass times velocity. So the mass is 1.67 times 10 power negative 27 times the velocity. The velocity of the particle initially is 500. So this is times 500 meters per second. I press my calculator. 500, 1.67 exponent negative 27. So the momentum is 8.35 times 10 power negative 25. State an expression in terms of m, Va, Vb of the total momentum of A and B after the collision. State an expression in terms of m, Va, so m being the mass. So total momentum of A and B after collision in the x direction. So after collision in the x direction, we are going to resolve Va in the x will be Va cos 60. Vb in the x will be Vb cos 30. So the momentum in the x is going to be mass times this mass of A. Of course, the particles, they have the same mass. So I'll just say m times Va cos 60 plus m times Vb cos 60. So the expression is going to be m Va cos 60 degrees plus m Vb cos 30 degrees. That is the expression. Then in the y direction, Note that in the y direction, B moves downwards and A moves upwards. So they're in opposite directions, so we shall subtract. I have to resolve V in the vertical, and to be VA sine 60 upwards, and here we shall have VB sine 30 downwards. So we shall subtract these two. So the momentum in the vertical will be M VA sine 60, that is upwards, minus M VB sine 30, which is downwards. So that is the expression for momentum. Then calculate the magnitude of the velocities VA and VB after the collision. VA and VB after collision. So we can consider conservation of momentum, and I will start with horizontal momentum. Horizontally, initial momentum was the mass, which is m for the particle, times the speed, which is 500. That is for A. The other one was at rest. Although I have the total initial momentum, I just want to use this so that m will cancel out. Then after collision, we are in the x direction. In the x direction, after collision, I have m VA cos 60 plus m VB cos 30. So you notice that m is a common factor, so it has cancelled out. M is a common factor, it has cancelled out. And as a mathematician, you notice that 500 is equal to, because you're a mathematician, the cos of 60, I think the cos of 60 is the same as the sine of 30. The cos of 60 is a half. The cos of 30 is root 3 over 2. So I want to simplify my life. So this is going to be VA divided by 2, because the cos of 60 is a half. Then m, remember m has cancelled out because it was a common factor. So that is VA over 2 plus the cos of 30 is root 3 over 2. So this is going to be VB root 3 over 2. That is one equation. I consider momentum in the vertical. Initially in the vertical, momentum is 0 because the particle was moving horizontally. There was no particle moving vertically initially. But after collision, momentum is now this one in the y direction, which is m VA sine 60 minus m VB sine 30. Note that m has cancelled, and it means, remember, sine 30 is root 3 over 2, and that is sine 60. Sine 30 is a half. So I will have 0 equaling to VA root 3 over 2 minus m has cancelled out because it's a common factor, and the other side it is 0. So minus a VB divided by 2, because sine 30 is a half. I'm just trying, you can use any mathematical method that you think is easier for you. So you will notice that actually VB is the same as VA times root 3 from this equation here. VB is the same as VA times root 3. I will go back to equation 1 and substitute for VB. So this implies that 500 is equal to VA over 2 plus VA root 3 times root 3. This is divided by 2. Okay, so root 3 times root 3, I think that is 3 over 2. You can just cross multiply by 2. You multiply everything by 2, so this is 1000 equals to VA plus 3 times VA. Root 3 times root 3, that is 3, because it will be root 3 squared, and the square cancels the square root. So I've multiplied just everything by 2. That's why you see 1000 this side. So I know VA plus 3VA, that is 4VA. So I have 1000 divided by 4. That means VA is 250 meters per second. So VA is 250 meters per second. Then I have to find the VB. VB is very easy. VB is equal to VA times root 3. So that is 250 root of 3. And this is 433.0. So I'll just write 433. So those are the values of VA and VB. I've used some mathematical concepts that I may think some people may not be having ideas about, but it's okay. You can use any mathematical principles that you think you're familiar with. State Newton's first law. We have said an object or a body stays at rest or continues moving with a uniform velocity unless acted upon by a resultant force. So a body stays at rest or continues moving with a uniform velocity unless acted upon by a resultant force. I say the word resultant is very important in that law because the resultant force causes acceleration, it affects the velocity. An object of mass 100 grams is moving in a straight line with a velocity 0.6 to the right. An object B of mass 200 grams is moving in the same straight line as an object A with a velocity 0.8 to the left. The other one was moving to the right, this is moving to the left. Objects A and B collide. Object A then moves with a velocity of 0.4 to the left. In other words, object A rebounds in that direction, and object B, we don't know. Calculate the magnitude of the velocity of B after the collision. So we know that momentum is mass times velocity. So we are going to conserve momentum. Total momentum before collision, it should be equal to total momentum after collision. So total momentum before collision, I will not change the mass because I know the grams will cancel out, but you can still change if you want. So the mass is 100 times the velocity is 0.60. That is for A, minus, because B was moving initially in the opposite direction, so this is going to be 200 times 0.80. Note the minus here. I'm finding total momentum, but the minus is because the velocity is in the opposite direction. This should be equal to the total momentum after collision. I'm very sure for A it rebounds to the left. So its mass is 100 times its velocity, which is 0.4, but to the left, so I will say it is negative 0.4, plus B, its mass is 200 grams, but I don't know its velocity, I'm calling it V. So I'll just simplify this. 100 times 0.6 minus 200 times 0.8. So this is negative 100. That's negative 100, but I have 100 times 0.4. So this is going to be plus 40 because this is 40, negative 40. Then on the left I have 200 times V. So V is going to be negative 60 divided by 200. So 60 divided by 200, I think that is 0.3. So this is going to be negative 0.3. It is negative 0.3. Of course, the negative simply means that B also moves to the left. It moves towards the left. That's what the minus here is showing. Because velocities to the right have been assigned positive, velocities to the left assigned negative. The collision between A and B is inelastic. Explain how the collision is inelastic and still obeys the law of conservation of energy. It is going to be inelastic simply because kinetic energy is not conserved, but the kinetic energy is not lost, it is just transferred to other forms. So the law of conservation of energy is still, so energy is still conserved. You can also see that the collision is inelastic by checking the relative velocities of approach and separation. You can check. And if relative velocities are not the same, then it means kinetic energy is not conserved. Approach relative velocity of approach is 0.6 minus negative 0.8, which I think is going to be 1.4. That is approach. Separation we have 0.4 is to the left, 0.3 is also to the left. So you can, they are on the same side. So I just say a negative 0.4 minus they are on the same side, and I just want the difference between them. So I'll say negative 0.4 minus 0.3, which is going to be equal to 0.7 on the same side. So the collision is inelastic because kinetic energy is not conserved. So I will simply say inelastic since kinetic energy is not conserved. Inelastic since kinetic energy is not conserved. That's number one. However, how is it obeying the law of conservation of energy? The kinetic energy is not conserved, but kinetic energy is simply transferred to other forms. So energy is conserved. Total energy is still conserved. So kinetic energy is not conserved, but it is transferred to other forms such as heat. It is transferred to other forms such as heat. So the law of conservation of energy is obeyed. So the law of conservation of energy is still obeyed. State Newton's second law of motion. Of course, the second law is the easiest. The net resultant force is directly proportional to the rate of change of momentum. Resultant force the resultant force is directly proportional to the rate of change of momentum and the two act in the same direction. The resultant force is directly proportional to the rate of change of momentum, and the two act in the same direction. That's the law of conservation, the Newton's second law of motion. A constant resultant force F acts on an object A. The variation with the time t of the velocity v for the motion of A is shown here. So here we have velocity against time. Velocity against time, and it is a straight line starting from this point here, and it is stopping at this point here. The scale on the vertical is 5 minus 4 divided, that is 1 over 10 to 0.1. So this is 4.2, and here it is, I think, 8.8. Okay. The mass of A is 840 grams. Calculate for the time t equals to 0 to t equals to 4, the change in momentum. So momentum is mass times velocity, so the change in momentum will now be the mass times maybe v2 minus v1, the change in velocity. So this is going to be, the mass is 840, which is 0.84 in kilograms. Then the change in velocity between t equals to 0 to t equals to 4, that is 8.8 and 4.2. So I will say 8.8 minus 4.2. So 8.8 minus 4.2, I multiply this by 0.8, and this gives me the change in momentum as 3.9 kilogram meters per second. Then the force. Remember, we have already defined force as the rate of change of momentum. So since the force is the rate of change of momentum, this will be 3.9 divided by change. The time is from 0 to 4, so that is 4.0. And from my calculator, so this is going to give us a 0.975. 0.975 as the force. Okay, let me check this again. 8.8 minus 4.2 times 0.84. Okay, 3.9. Okay, so this is 0.975 or 0.98, whatever. The force F is removed at t equals to 4. Object A continues at a constant velocity before colliding with an object B as illustrated in the figure here. So A continues with a constant velocity before it collides with object B that was at rest. Object B is initial at rest. The mass of B is 730 grams. The objects A and B join together and have a common velocity of 4.7. By calculation, show that the change in momentum of A and of B during the collisions are equal and opposite. They said by calculation. Let's start with A. Remember, momentum is mass times velocity, and the change in momentum will depend on the change in the velocity of a particular body. So we'll start with A. Change in momentum for A. Its mass is, the mass was 840 grams, which is 0.8. So that is 0.84. And its velocity, its change, because they move together, they move with a common velocity, 4.7, that is the final velocity. But its initial velocity is, because it continues at a constant velocity before it collides, that is after 4 seconds, the velocity is 8.8. So it continues with 8.8 before it collides. So its change in momentum is going to be, starting with the final velocity, 4.7 minus 8, 0.8. When I press my calculator, 4.7 minus 8.8 times 0.84. This is giving me a negative 3.44, which is approximately negative 3.4 Newton seconds to two significant figures. Let me check the change in momentum for object B. The mass is 730 grams, which is 0.73 times. The final velocity is 4.7, but remember it was initial at rest, so this is minus 0. So I say 4.7 times 0.73. This is giving me positive 3.43, which is approximately 3.4 Newton seconds. Although the magnitudes are different, although the signs are different, the signs just show that they're in opposite directions. The change in momentum is actually the same, because they said show that the changes in momentum of A during the collision are equal but opposite. So the sign is showing they're in opposite directions. So hence, magnitude is the same. Magnitude is the same, but in opposite directions, as shown by the negative sign. So one is positive, one is negative, meaning that they are in opposite directions. So explain how the answers obtained in Roman 1 support Newton's third law. Remember Newton's third law? The force on body A by body B is equal but opposite the force on body B by body A. So the change in momentum for A is equal and opposite to the change in momentum for B. That's number one. Remember, force is the rate of change of momentum. If the change in momentum is equal but opposite, then the forces are equal but opposite. So change in momentum for A is equal and opposite to change in momentum for B. But remember, force is the rate of change of momentum. Force is the rate of change of momentum, or is change in momentum over time. And remember, when they come into contact, the time of collision is the same. So just to take you mathematically, they have told us the change in momentum is equal but opposite. Force is the rate of change of momentum. If the change in momentum for A is equal and opposite the change in momentum for B, and yet the time is the same, then it means the force on A is equal and opposite to the force on B. So the force on A by B is equal and opposite to the force on B by A. That is Newton's third law. So even if I stop here, the 2 marks are exhausted. By reference to the speeds of A and B, explain whether the collision is elastic. by reference to the speeds. So we look for the relative speeds of approach for A and B. Initially, this was moving at 8.8, the other one is at rest. Relative speed of approach is 8.8 minus 0. Then relative speed of separation, because they move with a common speed, the relative speed of separation is 0. Relative speed of approach is that. Relative speed of separation, because they stick together, relative speed of separation is 0. So it means it is inelastic. So inelastic the reason is very simple. Relative speed of approach is not equal to relative speed of separation. State what is meant by the mass of a body. Of course, right from lower classes, maybe you define mass as a quantity of matter contained in a substance. But mass is a property of a body resisting change in motion. So it is a property of a body resisting change in motion. A property of a body resisting change in motion, that is mass, or you can define it as a quantity of matter. Quantity of matter in a substance. That is mass. Two blocks travel directly towards each other along a horizontal frictionless surface. The blocks collide as illustrated here. So we see that we can say velocities to the left are positive, 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 that is to the right, to the left negative. So they have given us block A mass 3m, block B mass m. Before the collision, block A moves to the right with a speed of 0.4 and block B moves to the left with a speed of 0.2. After collision, A moves to the right with speed of 0.2, B moves to the left to the right with the speed of v. Use Newton's third law to explain why during the collision the change in momentum of block A is equal and opposite the change in momentum of block B, that is during collision. Remember, the time of collision is the same. So by Newton's third law, force on block A by block B is equal but opposite to force on block B by block A. That is by Newton's third law. We also know that force is the rate of change of momentum. Force is the rate of change force is the rate of change of momentum and since time of collision or time of contact is the same, the change of momentum of A is equal and opposite to the change of momentum of B. And since time of contact is the same, so it means the change in momentum of A is equal and opposite to that of B. So you can think about this in mathematical terms. For example, the force on A is equal but opposite to the force on B. And force, remember, is the rate of change of momentum, which means change in momentum of A with the time is the same as change in momentum of B with the time. And since the time is the same, so T cancels out. And if T cancels out, it means change in momentum of A is equal to negative change in momentum of B, because T is the same. The negative shows that they are in opposite directions. Determine speed V. So we are just going to use conservation of momentum. I always prefer to begin by writing momentum is mass times velocity. So total momentum before collision, the mass is 3m, the speed is that, the mass is this, but this is in the opposite direction, so we shall have 3m times 0.04 minus, because the other one is in the opposite direction, m times 0.25. Sorry, this is 0.4 times 0.25, that is total momentum before collision, should be equal to total momentum after collision. The mass is 3m for A, and its speed is 0.20 plus the other one is m, and its speed is v. So you see that m is a common factor, so it has cancelled out. And if m has cancelled, I will just combine this. So I have 3 times 0.4 minus 0.25 minus 0.6. So this is giving me as 0, v as 0.35. So the answer here is 0.35. Remember, m has cancelled out because there's a common factor everywhere. Calculate for the blocks the relative speed of approach. We just subtract. So it is 0.4 to the left minus to the right minus negative 0.25 to the left. So the relative speed of approach is 0.40 minus negative 0.25. So the negative minus negative, that becomes plus, which gives us 0.65. Speed of separation, they are both to the same side, so I have 0.2 minus v was 0.35, or the other way around, 0.35 minus 0.2. Since they are in the same direction, I don't need to add a negative. So it is 0.35 to the right minus 0.20 still to the right. And this gives me a 0.15. That is the relative speed of separation. Use your answers to state and explain whether the collision is elastic or inelastic. Of course, this is inelastic. Reason: relative speed of approach is not the same or not equal to relative speed of separation. Relative speed of approach is not equal to relative speed of separation. To study the principle of conservation of momentum. So we know that total momentum of a system of interacting or total momentum of an isolated system of interacting bodies is always constant. Total momentum of an isolated system of interacting total momentum of an isolated system of interacting bodies is always constant. So the word isolated here is very important, or you can replace it with a closed system. So that is the principle of conservation of momentum. Simply make it part of you and you don't need to think about it much. A stationary firework explodes into 3 different fragments. It just explodes. That means its initial momentum is 0. It explodes into 3 different fragments that move in a horizontal plane as illustrated. So they move in that plane. So we have here the x, which are just, because it's a horizontal plane, like you have a paper on your table, that's a horizontal plane. But then we shall divide this into an x direction and a y direction. So AB is x direction, so we can also have the vertical direction or the y direction. So the fragment of 3m has velocity 7, that is upwards. Another one of 2m mass has a velocity of 6 at an angle theta. Another one of 1.5 has velocity 8 at an angle theta to a line AB. Use the principle of conservation of momentum to determine theta. So we can conserve momentum in any of the directions. If you try to conserve momentum horizontally, you will not be able to find theta, because on the left, momentum in this direction, the x direction, here we have 2.0 m times 6 cos theta. The other side we have 8.0 times sorry, we can this is 1.5 times 8 cos theta. So these are equal. In the horizontal, they are just going to be equal. So cos theta is going to cancel out. So that doesn't make any sense. So we are now going to consider conservation of momentum in the vertical. Momentum should also be conserved vertically. In the vertical upwards, we have momentum, which is this mass times that velocity in one plane. So momentum equals to mass times velocity. By conservation of momentum, 3.0 m times the speed, which is 7.0, should also be equal to 2.0 m That is, I'm considering this ball here. 2.0 m times this speed in the vertical is going to be 6 sine theta. So this will be times 6.0 sine theta, that is downwards, plus the momentum of this one should also be downwards, and this speed is going to be 8 sine theta, also downwards. So this will be plus 1.5 m times 8.0 sine of theta. So just simplify this. So this side I have 21 m. M has cancelled, it is a common factor everywhere, so m cancels out. So I have 21 equals to 2.2 times 6, that is 12. 1.5 times 8, I think it's also 12. So this is 12 and that is 12, giving us 24 sine theta. So 21 divided by 24, so sine theta is 21 over 24. Then what is theta? Theta is the sine inverse. Sine inverse. So this is 61.04, or approximately 61 degrees. So that is theta. Calculate the ratio kinetic energy of fragment of mass 2.0 m over kinetic energy of fragment of mass 1.5. Remember, kinetic energy EK is a half mv squared. So we now find a ratio for a fragment of mass 2.0 m. So this is going to be a half. The mass is 2.0 m. Then its speed. Let's see if its speed. Its speed is 6.0, so that is times 6.0 squared. Do not resolve speeds when you're finding energies. Divide by a half. Then the mass of 1.5 m times its speed is 8. So that is 8.0 squared. So this gives us 6.0 times 2 divided by 1.5 times 8.0 squared. So this gives me 0.75. So the ratio is 0.75. Ball is thrown vertically upwards towards a ceiling and then rebounds as illustrated in that figure. The ball is thrown with a speed 9.6 meters per second and takes time 0.3 to reach the ceiling. It takes time 0.3 to reach the ceiling when its initial speed is 9.6. The ball is then in contact with the ceiling for a further 0.085 seconds until leaving it with a speed of 3.8 meters per second. The mass of the ball is 0.056 kilograms. Assume air resistance is negligible. So equations of motion can apply because the acceleration will be the acceleration due to gravity. Show that the ball reaches the ceiling with a speed of 6.0 meters per second. This is basically kinematics. So V is equal to U plus AT. And this is going to be our initial velocity is 9.6. Because it's moving upwards, acceleration is going to be minus 9.81. Then the time it takes to reach the ceiling is 0.37. So this is times 0.37. I just press my calculator. 9.6 minus 9.81 times 0.37. So this is giving me 5.9703, which is approximately 6.0 meters per second to two significant figures. Calculate the height. Calculate the height of the ceiling above the point from which the ball was thrown. So I need an equation which will give me height. So basically, you can choose to use v squared equals to u squared plus 2as. Since we now know the velocity with which it reaches the ceiling, method number 1, v squared equals to u squared plus 2as. So it reaches the ceiling with a speed of 6, so 6 squared is equal to initial velocity 9.6 squared minus, because it's going upwards, so it will be minus 2 times 9.81 times the displacement s, which is the height. So I find s, which is the height, so that is 6 squared minus 9.6 squared divided by negative 2 times 9.81. So I'm finding s as 2.9 meters to two significant figures. So this is 2.9. So that is method 1. Method 2, you can use s equals to ut plus a half at squared. So s is going to be equal to u times t. U is 9.6 times 0.037 minus a half times 9.81 times t, which is 0.037 squared. When you press your calculator, you should be getting the same answer as 2.9. So this is method number 2. Calculate the increase in gravitational potential energy of the ball for its movement from its initial position to the ceiling. Increase in gravitational potential energy from its initial movement from its initial position to the ceiling. So that is very easy. The increase in potential energy is going to be mg times the increase in the height h. So this is going to be the mass was given. They gave us the mass as 0.056. G is 9.81 times the increase in height, which is 2.9. And of course, when you press your calculator, this is 1.6 joules. Calculate the decrease in kinetic energy of the ball while it is in contact with the ceiling. Decrease in kinetic energy. So the decrease in kinetic energy while it is in contact with the ceiling, we shall just look at the kinetic energy when it arrives at the ceiling and the kinetic energy when it leaves the ceiling. That is, there should be a difference there. So we know that kinetic energy EK is equal to a half mv squared. So the decrease in kinetic energy is going to be equal to a half. The mass of the ball is 0.056. There is a change in v squared. So it arrives at the wall, at the ceiling with the speed 6. So initial kinetic energy will be 6.0 squared. It leaves the ceiling with the speed, they told us it leaves the ceiling with a speed of 3.8. So the kinetic energy with which it leaves the ceiling is depending on 3.8 squared. So I get the difference here to get the decrease in kinetic energy. So the difference there is 0.60. Please, it's wrong to say 6 minus 3.8 and then squared. That is wrong mathematics. Here we are getting kinetic energy when it arrives minus kinetic energy when it leaves. Each of these has v squared. It's not difference in v then squared. This is wrong mathematics. State how Newton's third law applies to the collision between the ball and the ceiling. Of course, the force on the ceiling by the ball the force on the ceiling by the ball is equal to the force on the ball by the ceiling, but in opposite direction. So the force on the ceiling by the ball is going to be equal to the force which is exerted on the ball by the ceiling, but it will be in the opposite direction. That is in accordance to Newton's third law. State the change in momentum of the ball during collision. Remember, momentum is mass times velocity. So we want the change in momentum. And the change in momentum is going to be the mass. The mass of the ball is 0.056. Then the change in velocity, it arrives at the ceiling with a speed of 6.0, then to rebound. So this will be negative, minus negative 3.8. Momentum is a vector quantity. That's why you see I have a negative here. Here, kinetic energy is a scalar quantity. I didn't mind about the direction. That's why I did not put negative on V. But even if kinetic energy is a scalar quantity, the direction of V does not affect the kinetic energy. But for momentum, I put the negative. When I press my calculator, so I'm getting the change in momentum as 0.55. Determine the magnitude of the average force exerted by the ceiling on the ball during the collision. The average force exerted by the ceiling on the ball during the collision. First of all, we can find the resultant force on the ball when it collides with the ceiling. The resultant force. The resultant force is given by the rate of change of momentum in accordance to Newton's second law. So the resultant force on the ball is equal to the resultant force on the ball. Resultant force on the ball F is equal to the rate of change of momentum, which is going to be 0.55 over the time of contact. The ball was in contact with the ceiling for a time of 0.085 seconds. So this will be over 0.085. When I press my calculator, so this is 6.47 newtons. That is the resultant force on the ball. But then remember, the resultant force, when this is the ceiling and the ball is hitting on the ceiling, there is two forces acting. Number one, the force exerted on the ball by the ceiling, and number two is the weight of the ball. These ones are acting in the same direction. So the weight, this is the force by the ceiling, and then the weight, they act in the same direction. That means the resultant force is equal to the sum of these two forces. So it means 6.47 is equal to the force by the ceiling plus the weight of the ball, which means that the force by the ceiling is going to be equal to 6.47 minus the weight. 6.47 minus the weight, which weight is mass times gravity, which is 0.056 times 9.81. So just subtract 6.47 minus 0.056 times 9.81. So this gives us 5.9. 5.9 newtons. Ball X slides along a horizontal frictionless surface towards a stationary block Y as illustrated. In the figure, we have momentum 0.4 for X, Y is stationary, so its momentum is 0 initially. There are no resistive forces acting on the block X as it moves towards Y. At t equals to 0, block X has that momentum. A short time later, the blocks collide and then separate. The variation with time t of the momentum of block Y is shown here. Of course, this graph should start from 0 because Y was initially at rest. So the variation of the momentum is shown here. It was initial at rest, so initial momentum is 0. I'm going to increase the thickness. So the define linear momentum. Of course, linear momentum is mass times velocity. Product of mass and velocity. I'll just write mass times velocity. Then use the figure to determine the time interval over which the blocks are in contact with each other. So when contact occurs, they must exchange momenta. So at t equals 60, before t equals 60, momentum is constant. Then it starts increasing, and then it stops increasing after at t equals to 100. So the time interval is between 100 and 60, which gives us 40 milliseconds. Describe without calculation the magnitude of the acceleration of block Y from t equals to 80 to t equals to 100. From the graph, you see that between t equals to 80 to t equals to 100 is a straight line, and we are determining acceleration. Force is equal to mass times acceleration, and force is the rate of change of momentum. Between t equals to 80 to t equals to 100, you see it is a straight line, meaning that the gradient is constant, of course not 0. So since it is a constant gradient, the force is constant, the acceleration is constant, but remember it is not 0. So here we can say they said describe without calculation the magnitude. So the acceleration here is constant simply because the gradient is constant. They didn't ask us to explain anyway. Then t equals to 100 to t equals to 120. From the graph, you see t equals to 100, t equals to 120. It is a straight line. It's a straight horizontal line whose gradient is 0. So the force there is going to be 0, meaning the acceleration is equal to 0 because force is ma. It is 0 because it is a horizontal line. Gradient is 0. There is no change in momentum. So here we shall say this is 0. That is 0. There is no change in momentum. That is the explanation. No change in momentum. The gradient is 0. Okay. Use the figure to determine the magnitude of the force exerted by block X on block Y. So we just look for the gradient. Of course, we know that force is equal to the rate of change of momentum, which is going to be the gradient. So we go here. The time interval of which they are in contact is 40, and the change in momentum is from 0 to 0.5. So I'll just say 0.5 minus 0 over the time interval, which is 40 times 10 to the power negative 3, because it was in milliseconds. And when I press my calculator, 0.5 divided by 40 exponent negative 3. So this gives me 12.5. Remember, force is the rate of change of momentum, which is, in this case is the gradient. Then on the figure, sketch the variation of the momentum of block X with the time t equals to 0 to t equals to 160. I want you to remember block X was the one which was initially moving and block Y was at rest. By the principle of conservation of momentum, total momentum should remain the same. Total momentum should remain the same. Initial momentum of block X is 0.4. And before it changes, before it collides with Y, it remains 0.4. So it means it only changes after collision. So we shall draw a horizontal line at 0.4, not until we reach 60 milliseconds. So I'll put here my ruler. So that is initial momentum of block X. And total momentum should remain the same, and is going to be total momentum should be 0.4, because the other one was initial at rest. Therefore, since this one has gone to 0.5, the other one should fall down by one step, so that below the x-axis, so that total momentum remains 0.4. So it means this one should go down. When the other one goes to 0.5 upwards, this should go up to negative 0.1. So it should come up to here. Negative 0.1. And when the other one remains constant, even this one remains constant. So we shall have a horizontal line. Okay, so this is going to be the graph. Just a moment. Okay, so this is what we had. And I think these graphs are now very easy. You notice that the only unique thing about them is that actually when one raises by a certain value, the other one falls down by a certain value. And they are always constant at the same time. They always constant at the same, they start being constant at the same time. So at 100 milliseconds, momentum of block Y remains constant, meaning that it's because the momentum of block X is also constant. Between 0 and 60, momentum of block Y was 0 and constant because there was collision had not started. The other one had momentum of 0.4 and remained constant until collision started. Okay, so that is that particular question. A cylindrical disc of mass 0.2 kilograms has a circular cross-sectional area A as shown in the figure. The disc is on horizontal ground as shown in the figure 3.2. A force X of magnitude 8.9 acts on the disc in a direction of 30 degrees to the horizontal. The disc moves at a constant speed of 0.6, that means the acceleration is 0, along the ground. Determine the rate of doing work on the disc by the force X. The rate of doing work, that is power. Power, remember, is work done over time taken. work done is force times distance over time, and the distance in a specified direction over time is distance over time is going to be the velocity. So the power is going to be force times the velocity. So the force in the horizontal direction, the force is going to be, we are going to resolve this in the horizontal. Bringing this in the horizontal, it is going to be 8.9 cos of 60. So the force is 8.9 cos, not cos 60, cos 30. That is the force. Then times the velocity, which is 0.60. So we just resolve the force in the direction of the velocity. So 8.9 cos of 30 times 0.6. So this gives me the force, the rate of doing work as 4.6 watts. That one we saw in work, energy, and power. The force X and the weight W, the weight of the disk, exert a combined pressure on the ground of 3,500 pascals. Calculate the cross-sectional area A of the disk. Remember, pressure is force over area. The force X and the weight of the disk exert a combined pressure of that on the ground. Pressure is the force acting normally per unit area. So we need the force. Of course, we need the force acting normally. It means we have to resolve X vertically, and X resolved vertically is 8.9 sine of 30 plus the weight, that is the force causing the pressure. So it means the total force, F total, is going to be 8.9 sine of 30 plus the weight, which is M times G. That is the total force causing the pressure, or 8.9 sine of 30 plus the mass, which is 0.2, 24 of the disk, times G, which is 9.81. And I think this is 8.9 sine 30 plus 0.24 times 9.81. So the force exerting a pressure is 6.80 newtons. That is the force. So it means area is going to be the pressure, the force divided by the pressure, which is going to be, the force is 6.80 divided by the pressure, which is 3,500. So I divide. So this gives me 1.9 times 10 power negative 3. 1.9 times 10 power negative 3 meters squared. Newton's third law describes how forces exist in pairs. One such pair of forces is the weight of the disk and another force y. State the direction of force y. So since the forces exist in pairs, if the weight is downwards, then the force y is going to be upwards. Then the name of the body on which the force y acts. If the weight is exerted on the ground, then force y acts on, the name of the body on which force y acts. Note that force y is upwards. The weight of the body is acting downwards. So state the name of the body on which force y acts. So force y must be the planet, or it is going to be the earth for this matter, because the weight of a body is the pull of gravity on the body by the earth. That means if y is upwards, then y is the force on the earth away by the body anyway. So this is going to be acting on the planet or on the earth. Okay. The figure shows the velocity time graph for an object moving in a straight line as shown here. Determine an expression in terms of u, v, and t for the area under the graph. So we can try to find area. I'll divide this into 2. And this part here, this is time, this is 0 to t. So this is going to be u times t. This part here is a triangle, so this is a half into this distance is v minus u, then times t. So area is equal to ut plus a half into v minus u times t. So that is the area. If you want, you can simplify this further, but that is ut plus a half into v minus u times t. State the name of the quantity represented by the area under the graph. Of course, this represents the displacement because this is a velocity time graph. So this is displacement. The ball is kicked with a velocity of 15 meters per second at an angle of 60 degrees to the horizontal. The ball then strikes a vertical wall at the instant when the path of the ball becomes horizontal. That is the most important point. The path becomes horizontal when the ball has reached its maximum height. Okay? Assume that air resistance is negligible. By considering the vertical motion of the ball, calculate the time it takes to reach the wall. So V is equal to U plus 8. I'm considering vertical motion. So I have to resolve at the maximum point, V is going to be 0. Remember they said it hits the ball when the path becomes horizontal. It means it has reached maximum height. At maximum height, V is 0 in the vertical. Initial velocity in the vertical will resolve 15 vertically, which will be 15 sine of 60. Since it is moving against gravity, this will be minus 9.81 times t. So t is going to be 15 sine 60 divided by 9.81. And from my calculator, this is 1.3. Explain why the horizontal component of the velocity of the ball remains constant as it moves to the wall. Of course, we know there is no force in the horizontal. So there is no resultant force in the horizontal. There is actually no force in the horizontal. The only force acting is that due to gravity because air resistance was negligible. So there is no force in the horizontal direction. Since there is no force in the horizontal direction, there is no acceleration, so the velocity does not change. Show that the ball strikes the wall with a horizontal velocity of 7.5. We resolve horizontally. So V in the horizontal, Vx in the horizontal is going to be 15 cos 60. 15 cos 60, I think that is automatically 7.5. You can verify. Alternatively, you can say V in the x is going to be 15 sine of 30. Sine of 30, 15 of sine of 30 is 7.5. The mass of the ball in B is 0.4 kilograms. It is in contact with the wall for 0.12 seconds and rebounds. If we say rebounds, it moves in the opposite direction after collision. It rebounds with a velocity of 4.3. So 4.3 is just in the opposite direction. It is arriving at the wall with 7.5 in the horizontal. Use the information in B part 2 to calculate the change in momentum. Remember, momentum is mass times velocity. So the change in momentum is going to be the mass, which is 0.4. And then the velocity is changing. It arrives with 7.5 minus. Now this is in the opposite direction, so I'll put negative 4.3 because it rebounds. When I press my calculator, So from my calculator, this is 4.7 kilogram meters per second. Calculate the magnitude of the average force exerted on the ball by the wall. So force is the rate of change of momentum. So this is going to be the change in momentum is 4.7 and the time of contact was 0.12. And this gives me 4.7. So this is giving me 39 newtons. A ball falls from rest onto a flat surface, a flat horizontal surface. The figure shows the variation with the time t of the velocity v of the ball as it approaches and rebounds from the surface. So we see it approaches and rebounds from the surface. Okay, so this is a graph of velocity against time. So use data from the figure to determine number one, distance traveled by the ball during the time, the first 0.4 seconds. So 0.4 seconds, it is here. Velocity increases up to 4 meters per second. So I'll use, since initial velocity is 0, and this is, I'm going to assume that the motion is uniform. For the first 4 seconds, velocity increases uniformly, the acceleration is constant. So equations of motion can apply. So V is equal to, I think I'll use V squared equals to U squared plus 2AS. We want, it arrives after at 0.4 seconds, the velocity is 4.0 from the graph squared. Initial velocity is 0. The acceleration, a ball falls from rest onto a horizontal flat surface. So acceleration is going to be acceleration due to gravity. So this will be minus, it is falling, so that will be plus, not minus, because it is falling. So plus 2 times 9.81 times S. So I just find S. 4 squared divided by 2 times 9.81. So this is giving me S as 0.82. 0.82 meters. Then the change in momentum of the ball of mass 45 grams during contact of the ball with the surface. During contact of the ball with the surface. So remember, momentum is mass times velocity. It's always good to write the formula first. Then we want the change in momentum, which is the mass. The mass is 45 grams. 45 is 0.045 kilograms. Then the change in velocity. Let's check the velocities. So the average, we want to find the change in momentum of the ball of mass 45 grams during contact of the ball with the surface. So during contact of the ball with the surface, we notice that actually velocity is, we are starting at the point of contact. You see that here it is 4.2. I guess this is 4.2. And here it is negative. This is negative 3.6, I guess. Yes, negative 3.6. This is 4.2 at the points of contact. Contact starts when the velocity is 4.2 and stops when the velocity is negative 3.6. So it means the change in momentum is going to be 4.2 minus negative 3.6. From my calculator, 4.2 minus negative 3.6 times 0.045. So the change in momentum is 0.35. Then the average force acting on the ball, of course, that is easy. Average force. We know that force is equal to the rate of change of momentum. The rate of change of momentum, and this is 0.35 over time. Let's check the time of contact. So I will take between, let us say contact starts from around here up to this point. So what is the time interval between these two? The scale on the x is 0.1. So this is 0.43 minus 0.57. 0.57 minus 0.43, which is 0.14. So this time here is the time of contact with the wall. I started from the center, from this point here and this point here. So that is 0.14 seconds. Okay, so the time of contact is 0.14 seconds, which gives us so this is giving me 2.5 newtons. State the relation between force and momentum. We know that force is equal to the rate of change of momentum. Force is equal to the rate of change of momentum, that's the relation. A rigid bar of mass 450 grams is held horizontally by two supports, A and B, as shown in the figure here. Okay, we see a ball is falling on one end of the rigid bar. So we can see this is the center. Let's just do a few calculations here. A rigid bar of mass 450, its weight acts, let's assume that the weight acts at its center here. So here there is a force, which is the mass, that is 0.45 times gravity, 9.81. That is the weight of the bar at that point, at the center, if that is the midpoint. The support A is 45 centimeters from the center of gravity C of the bar, and support B is 25 from C. A ball of mass 140 grams falls vertically, so that is 0.14 in kilograms. It falls vertically onto the bar such that it hits the bar at a distance of 50 centimeters from C. We can see that from the diagram. Okay. The variation with the time t of the velocity v of the ball before, during, and after hitting the bar is shown here. So we have a graph of velocity against time, velocity downwards. Okay. So we see there is a time of contact where the velocity changes, that is between this value here and 0.6. That is the time, this is the time of contact. The scale on the x-axis is 0.2 divided by 10, 0.02. One small square is 0.02, so these are 2. So the time of contact there is actually 0.04 seconds. For the time that the ball is in contact with the bar, use the figure to determine the change in momentum. So we know that momentum is mass times velocity. The change in momentum is going to be the mass. We want the momentum of the ball. So mass of the ball, which is 140 grams, that is 0.14 kilograms, times the change in velocity. Velocity changes between, here it is in the center of this box. which I think is 5.5, because the scale on the vertical is 0.2. So 4.2, 4.4, 4.6, 4.8, 5, 5.2, 5.4, 5.5. So that velocity is 5.5 up. Then at the bottom it is exactly -4. So this is going to be 5.5 minus -4. And from my calculator, so this is 1.33. Again, for the time that the bar is in contact with the ball, the ball is in contact with the bar, use the figure to show that the force exerted by the ball is 33 newtons. Remember, force is equal to the rate of change of momentum. The change in momentum is 1.33, and the time of contact we have just got as 0.04. Remember, this time here where the velocity is changing, this is the time of contact, which we have seen as there are two small squares, that is 0.04 seconds. So the force is going to be 1.33 over that, which when I press my calculator, this force is 33.3 newtons. For the time that the ball is in contact with the bar, use data from figure 3.1 and B Roman 2 to calculate the force exerted on the bar by the support A. So figure 3.1 is this one. So we want to find the force exerted on the bar by support A. The force exerted on the bar by support A, that is downwards. So we are going to take, we are going to take moments. Let's take moments about B. The force exerted by A is downwards, and the force exerted by the ball is also going to be downwards. This force here is going to be, they told us it was 33, so this is going to be 33 times the perpendicular distance, which is 50 plus 25, that is 75. That is the moment by the ball when it hits the bar. Then the moment here, of course, we also have the moment of the weight, which is going to be the moment of the bar, which is the weight times its perpendicular distance, which is 25. Then should be equal to, these two are going to cause anti-clockwise moments, but this one is causing clockwise, which is going to be F of A times its perpendicular distance, which is this distance here, that is 45 minus 25, which is 20. So this will be times 20. I've not changed the units of distance because I know the centimeters are cancelling. So just to solve this, taking moments about A, not about A, taking moments about B. So we have seen 33 times, or you can say 33.3. 33 times 5, that is for the ball, plus 0.45 times 9.81 times 25, that is the moment caused by the bar. Its weight is at the center at point C, should be equal to FA times the perpendicular distance, which is 20. And we just solve for FA. I'll just press my calculator. So this is 129 newtons, or approximately 130. The support B, we want to find the force exerted on the bar by support B. So we can go back here. The force here is downwards, which is 33 newtons. The force here is the weight, which is 0.4 times 9.81. Then the force this side, we have got it as 130 downwards. So 130 plus the force which is here plus 33 should be equal to the force exerted by the bar upwards. So we just sum up and see. So we shall say the force of B is equal to the total force downwards. Therefore, FB is upwards, remember, should be equal to 33 downwards plus 130, which is downwards, plus the weight of the bar, which is 0.45, that is the mass, times 9.81. So this is giving me a total of 170 newtons to two significant figures. You can also verify that. Okay, a ball is thrown against a vertical wall. The path of the ball is shown here. The ball is thrown from S with the initial velocity 15 meters per second at an angle of 60 degrees to the horizontal. Assume that air resistance is negligible. For the ball at S, calculate the horizontal component of velocity. Horizontal component. We just resolve 15 in the horizontal, which is going to be 15 cos of 60. And 15 cos 60, that is 7.5. Then its vertical component of velocity, so we resolve vertically, that is going to be 15 sine 60, 15 sine 60, 15 sine 60, that is 13 meters per second. The horizontal distance from S to the wall is 9.95, okay? The ball hits the wall at P with velocity that is at right angles to the wall. That means it has reached the maximum height. If it hits with a velocity that is at right angles to the wall, it means it has reached the maximum velocity. It has reached, the maximum height. It has reached the maximum height if it hits with the horizontal velocity. It has reached the maximum height. The vertical velocity has gone to 0. The ball rebounds to a point F that is 6.15 meters from the wall. So it rebounds to a point F. We can see it rebounds to a point F. Remember, it will be falling through the same vertical height. That means the time it has taken to reach P, it is going to be the same time it is taking to fall back F. Since time is a scalar and it is falling through the same vertical height, it is going to be the same time. Okay? Using your answers in A, calculate the vertical height gained by the ball when it travels from S to P. Vertical height. So we need an expression which has displacement. So V squared equals to U squared plus 2AS. S is going to be the vertical height. We are considering vertical motion. So since it reaches the wall with a horizontal velocity, it means final velocity in the vertical is 0. So 0 squared is equal to initial in the vertical, we have calculated it as 13 squared. Since it is moving against gravity, that will be minus 2 times g, which is 9.81 times the vertical height. So we get h. So h is 13 squared over 2 times 9.81. From my calculator, it is 8.61 meters. You can also verify. Show that the time taken for the ball to travel from S to P is 1.33. The time taken to move from S to P is 1.33. Since we now know the vertical height as 8.61, we can consider still vertical motion because the time is going to be the same. Or we can consider horizontal motion, no problem. Considering vertical motion, I'll write Vm for vertical motion, and I use V equals to U plus AT. Remember, when it hits the wall, final vertical velocity is 0. Initial is 13 minus 9.81 times T. So T is 13 divided by 9.81. And this is automatically 1.33 seconds. Alternatively, I can consider horizontal motion. And I use S equals to UT plus a half AT squared. S in the horizontal, when it arrives at P, is 9.95. Initial velocity in the horizontal, we calculated it as 7.5 times T plus a half. Acceleration in the horizontal is 0 times T squared. This part becomes 0. There is no acceleration in the horizontal. So T equals to 9.95 divided by 7.5. And it is 1.33. Show that the velocity of the ball immediately after rebounding from the wall is about 4.6 meters per second. Show that the ball immediately after rebounding is about 4.6 meters per second. So note that when it rebounds, it travels a horizontal distance of 6.15, but the time it takes to arrive is going to still be 1.33 because it falls through the same vertical height. So the time is the same since it falls through the same vertical height. Therefore, S equals to UT plus a half AT squared. I am considering horizontal motion. The horizontal displacement is 6.15. Initial velocity with which it leaves the wall is U. The time it is going to take is 1.33 to arrive to the ground. The other part is going to be 0 because acceleration in the horizontal is 0. So U equals to 6.15 divided by 1.33. And this is 4.62, which is approximately 4.6 meters per second. So I want just to make this clear. It falls through the same vertical height. So time is the same. The time it has taken to reach the vertical height is going to be the same as the one it takes to reach the ground. So the time is the same. Then the mass of the ball is 60 times 10 power negative 3. Calculate the change in momentum. Momentum is mass times velocity. The change in momentum is the mass is 60 times 10 power negative 3. The velocity, remember it rebounds. Let's say it arrives on the wall with a speed of it arrives from the on the wall with a speed of 7.5, and we have seen it rebounds with a speed of 4.6, so it's minus negative 4.6, which gives us so this is 0.73, or you would have got negative 4.6 minus 7.5, then times the mass, 60 times 10 power negative 3, which will give you negative 0.73. So this could give you the same magnitude. Of course, the negative would just imply that the change in momentum is in the opposite direction. The change in momentum of the ball is in the opposite direction to the change in momentum of the wall. Lastly, state and explain whether the collision is elastic or inelastic. Of course, you see that the velocity with which it arrives is not the same as the velocity with which it leaves. So it means kinetic energy is not conserved. So kinetic energy is not conserved. In other words, it is less after collision. Hence, inelastic. The collision is inelastic because kinetic energy is not conserved. It is less after collision. You can also check the relative speed of approach and relative speed of separation. They are not the same. Remember, the wall is not moving. So O, relative speed of approach, relative speed of separation is less than relative speed of approach. Hence, inelastic. The speed of separation was 4.6. The speed of approach was, what was the speed of approach? 7.5 in the horizontal. So the relative speed of separation is not the same. It is less than the relative speed of approach, so inelastic. So that is another way of thinking about it. Let this video stop here for now because of several circumstances, but it will continue. I hope you enjoyed this and see you in the last part 3 of dynamics. Thank you and stay blessed.